So in this example problem, we're going to compare the Tresca yield criteria to the von Mises yield criteria. So in this case, where it said we're asked to estimate the torque required to cause yielding in a 10 millimeter shaft with a yield strength of 140 megapascals. Okay, so we are given our yield strength and we're given the diameter of our shaft as being equal to 10 millimeters or 0.01 meters. All right, so our shaft. So what this would look like is if we have a shaft that has a torque being applied at both ends of the shaft. All right, that's going to create a. So if we took an element within our shaft, this element is going to have a shear stress within it due to those torques. All right, and that shear stress tau xy we can set being in the case of an applied torque, we know that it's equal to the equation the applied torque times R over J. Okay, so we know so that's going to be our state of our equation that we'll use to figure out what the shear stress would be equal to, and then we can use TR. So the torque we don't know. The radius we do know. It's going to be equal to 0.01 meters divided by 2. And then the polar moment of inertia for a circular section is equal to pi over 32 times the diameter to the fourth. Okay? So, all right. So the first thing we're going to do is we're going to use our Tresca yield criteria to determine what would be our allowed torque. All right. So for the Tresca yield criteria states that the maximum shear stress tau ms s, which is also the same thing as the tau Tresca, all right, would be equal to sigma 1 minus sigma 3 over 2. All right, and then that's going to be equal to half of our yield strength. Okay, so half of our yield strength in this case would be equal to 70 megapascals from the 140. All right, so then we can say that our maximum shear stress, based off of our stress element that we have drawn here, our maximum shear stress is going to be equal to tau xy. All right, in this case, so we can say that tau maximum shear stress is going to be equal to tau xy. All right, which is going to be equal to 70 megapascals. Okay? All right, and we said the tau xy was already equal to TR over J. All right, so to solve for T, we can rearrange the equation and we'll get T is going to be equal to 70 megapascals times J divided by R. All right, so if we plug in those values, we're going to get T is going to be equal to 70 times 10 to the 6th newtons per meter squared times J, which is equal to pi over 32 times 0.01 meters to the fourth. All right, and then it's going to be divided by 0.01 meters divided by 2. All right, so this ends up being, if we simplify all this down, we end up getting 70 pi over 16 Newton meters, which is going to be 13.7 Newton meters. Okay. So we can repeat this process for the von Mises case. Criteria, right? So in the von Mises case, right, it helps if we draw our Mohr circle. Right? So in the case of, in our case, based off of our stress element, all right, we have no normal stresses, all right, but we have a value of tau xy. So this is our tau xy here. This is tau xy minus tau xy. So if we draw our Moore circle based off of this case, all right, our first principal stress was going to be on the right-hand side, and our third principal stress will be on the left-hand side. Both of these are going to be equal to tau xy and minus tau xy for sigma p3. All right, so we can plug in to solve for our sigma von Mises, which we know is going to be equal to, give me a second here. So from early in the lecture, we had this equation here for sigma von Mises, so we can plug in our sigma p1, our sigma p3, and our sigma p2 term, which is just going to be equal to 0, into this equation. So we'll end up getting 1/2 times sigma p1, which is just going to be equal to tau xy squared, plus sigma p minus negative tau xy for sigma p3 squared, and then we get plus minus tau xy minus tau xy for sigma p3 minus sigma p1 squared. So if we end up evaluating all that, we get our sigma von Mises is going to be equal to the square root of it's going to be equal to tau xy plus 4 tau xy, so it's going to end up being 1/2 times 6 tau xy squared, which will end up being equal to radical 3 times tau xy for our sigma von Mises. Okay, so we know that if we know that we can set our sigma von Mises equal to the yield strength at the point of failure, so we know that, and we know that tau xy we can plug in as being equal to TR over J. So if we plug all this in here, we can use this equation to solve for T. So if we take this equation here, we're going to solve for T, so rearrange it to solve for T. So we'll get T is going to be equal to SY times J over R and over radical 3. So if we plug in everything, we get 140 times 10 to the 6th newtons per meter squared for the yield strength times J, which is equal to pi over 32 times 0.01 meters to the 4th. And then we're going to get our denominator is going to be radical 3 times 0.01 meters divided by 2. Right? If we plug in all of our numbers and we evaluate everything, what we end up getting is we get 15.9 Newton meters. Right? So really quick to recap here, based off of our two criteria, if we needed to calculate the maximum torque that could be applied to this shaft, the von Mises criteria stated that the maximum torque you could submit was about 13.7 Newton meters, while the maximum torque for the von Mises case was 15.9 millimeters. So it's about it's a little bit more than 10% higher in the case of the von Mises stress. So this is just to illustrate to you the differences in the predicted maximum allowable torques or applied loads that you could apply to the same system, depending on which criteria you choose to use for your design.